By our best estimates, a calculation that takes Willow under 5 minutes would take the fastest supercomputer 10 to the 25 years. That's a 1 with 25 zeros following it, or a timescale way longer than the age of the universe.
Hi everyone, today we are going to talk about a revolution. Not the kind of marketing revolution we're sold every week, no, a true technological revolution that could change how we tackle humanity's biggest challenges. You know, for decades scientists have been talking to us about quantum computing, this somewhat crazy promise of a computer that would exploit the strange laws of quantum physics to perform calculations impossible with our current machines. For a long time, it seemed more like science fiction than anything else, but little by little, advances have accumulated. In 2019, Google had already made a splash with its Sycamore chip, which succeeded for the first time in outperforming classical supercomputers on a specific task. It was what is called quantum supremacy. A historic moment indeed, but still very limited in its concrete applications. Today, with Willow, we are taking an absolutely decisive step. To understand why, let me give you an image. Imagine you are trying to build a house of cards in a room full of drafts. That is roughly what quantum computing has looked like until now. The qubits, those famous quantum bits, were extremely fragile and lost their information in just a few microseconds. It was as if your castle systematically collapsed before you could finish it. What Google achieved with Willow is like finding a way to stabilize the room. They increased by 5 times the duration, qubits retained their information. From 20 microseconds, it went to 100 microseconds. It might seem tiny on our scale, but in the quantum world, it was huge, and the results are spectacular. To give you a concrete idea, a calculation that Willow can perform in less than 5 minutes would take, hold on tight. To put that in perspective, the universe is only 13.8 billion years old. So we're talking about a duration longer than the age of the universe. But beyond these staggering figures, what really makes Willow revolutionary is that it finally crosses the critical threshold of quantum error correction. It's a technical but crucial concept. It means that for the first time, we can efficiently correct errors that naturally occur in quantum calculations. It's like we finally have an autocorrect for quantum typos. This breakthrough paves the way for practical applications in critical fields. Imagine being able to perfectly simulate the behavior of molecules to create new medicines, or understand exactly how chemical reactions work to develop better batteries, more efficient solar panels, or even master nuclear fusion. In the video you are about to watch, Julian Kelly, the hardware director at Google Quantum AI, explained to us in detail how Willow works and what makes it so special. It's not just a more powerful new chip, it is potentially the key that will allow us to solve problems previously considered impossible. So, sit back comfortably, we're diving into the future of computing. A future where the lines between possible and impossible become increasingly blurred.
The systems behind our universe are quantum mechanical. They shift and change with the problems they're tasked to solve, exploring a vast array of options all at once. And like nature, quantum computing is responsive to the environments it works within, leading us to new breakthroughs for tomorrow's most challenging problems. Introducing our latest quantum computing chip, developed to learn and evolve like the natural world around us. Willow, from Google Quantum AI.
Hi, I'm Julian Kelly, Director of Hardware at Google Quantum AI. And today, on behalf of our amazing team, I'm proud to announce Willow. Willow is Google's newest and most powerful superconducting quantum computing chip, and the next step in our path towards building large-scale quantum computers and exploring their applications. I've been fascinated with quantum computing since I first experimented with qubits in 2008. And since coming to Google in 2015, it has been a dream to make our mission a reality, building quantum computers for otherwise unsolvable problems. We launched our first chip, Foxtail, in 2017, followed by Bristlecone in 2018 and Sycamore in 2019, which powered our milestone 1, the first quantum computer to surpass the best classical supercomputer on a computational task, random circuit sampling. Over the years with Sycamore, we have been able to squeeze a remarkable amount of performance from our hardware, including achieving a scalable logical qubit in our milestone 2. But we've ultimately been limited by quantum coherence times, the length of time qubits maintain their intended state. With Willow, we've made a huge step forward. We've increased quantum coherence times by a factor of 5, going from 20 microseconds in Sycamore to 100 microseconds in Willow. And we've accomplished this all without sacrificing any of the features that made our systems so successful. This advancement was enabled by our new dedicated superconducting quantum chip fabrication facility in Santa Barbara, one of only a few in the world. And we're seeing exciting developments coming from Willow, which has already surpassed Sycamore's breakthrough demonstrations. Our logical qubits now operate below the critical quantum error correction threshold, a long sought-after goal for the quantum computing field since the theory was discovered in the 90s. And we've achieved it for the first time with Willow. Errors are exponentially suppressed in our logical qubits, as error rates are halved each time we add physical qubits and scale from distance 3 to 5 to 7 surface codes. Additionally, our logical qubit lifetimes are now much longer than all of the lifetimes of the physical qubits that compose them. This means that even as we make our quantum chips larger and more complex by adding more qubits, we can use quantum error correction to actually improve their accuracy. We've pitted Willow against one of the world's most powerful supercomputers with the random circuit sampling benchmark. The results are pretty surprising. By our best estimates, a calculation that takes Willow under 5 minutes would take the fastest supercomputer 10 to the 25 years. That's a 1 with 25 zeros following it, or a timescale way longer than the age of the universe. This result highlights the exponentially growing gap between classical and quantum computation for certain applications. Let's talk about the hardware approach we've pioneered at Google Quantum AI that makes these things possible. Our tunable qubits and couplers enable super fast gates and operations to achieve low error rates, reconfigurability to optimize hardware in situ and run multiple applications, and high connectivity to efficiently express algorithms. We leverage this tunability to enable reproducible high performance across the device. Let me explain. A challenge in superconducting qubits is that not all of them are created equal. Some are outliers with uncharacteristically high errors. But here's where our tunable qubits really shine. We're able to fix these outlier qubits by reconfiguring them to perform in line with the rest of the device. And we can go one step further by having our researchers use tunability to continuously develop new calibration strategies that push errors down across all qubits with software. Let's quantify this and nerd out for a minute on quantum computer tech specs. We have number of qubits. Connectivity is the average number of interactions each qubit can perform with its neighbors. We quantify error probabilities for running simultaneous operations. Single qubit gates, 2 qubit gates, and measurement. Coherence time measures how long each qubit can retain its information. Measurement rate is how many computations we can run per second. And application performance is a full system benchmark. Willow hits a sweet spot across the full list. It has a large number of qubits with high connectivity and can run diverse applications. We measure low mean error rates across all operations with multiple native 2 qubit gates. We have greatly increased T1 times. We have very high measurement rates, and Willow is below the error correction threshold and performs random circuit sampling far beyond what is possible with classical computers. Looking to the future with Willow, we continue our journey towards building large-scale and useful error-corrected quantum computers that will push the boundaries of science and the exploration of nature. With future commercially useful applications in areas like pharmaceuticals, batteries, and fusion power, We are excited to solve the otherwise unsolvable problems of tomorrow.
There you go, you have just discovered Willow. And honestly, it's not just a slightly more powerful chip making headlines. No, on paper, it's truly a turning point in quantum computing history. Simply put, Google has achieved 3 absolutely incredible things. First, they made their qubit much more stable. No more house of cards collapsing every 20 microseconds. Then they crossed that famous quantum error correction threshold. Basically, their computations become truly reliable. And finally, they can adjust their chips in real time when something goes wrong, like a mechanic fixing a car while it's running. The numbers announced are completely crazy, as we've seen. Doing in 5 minutes what a supercomputer would take longer than the age of the universe to calculate, a very specific type of calculation, random circuit sampling. It's impressive, but it's still far from the practical applications we all dream of. In fact, that's a bit of the paradox of quantum computing. The more spectacular the announcements are, the more patient we must be to see concrete applications. What is really encouraging with Willow is that we are crossing technical barriers. A few years ago, we thought it was insurmountable. Quantum error correction was a bit like the holy grail of the field. Achieving it, even if it's still on a small scale, is already huge. Quantum computing was a somewhat crazy dream of scientists. With Willow, we are beginning to see this dream take shape, even though we are still far from being able to use it daily. It's like we are in 1950 for classical computing. The foundations are there, the potential is enormous, but it still requires years of development to make it useful for everyone. So yes, let's remain cautious in the face of spectacular announcements, but let's also keep that little spark of excitement. Because if even half of what Willow promises comes true, it could very well be the beginning of a new era in how we approach the great scientific and technological challenges of our time.